is going to be about, or this section is going to be about angles in triangles. So first thing, a triangle is, or a definition is, if a figure is a triangle, then it is formed by 3 segments joining 3 non-collinear points. Now, obviously, we all know what a triangle looks like, but we need to understand the labeling and the parts and things like that. If I wanted to refer to this triangle here, I use its vertices to name it. Those are our points there. So we would say that this is triangle A, B, C. That's how I would refer to that. Triangle A, B, C. Its vertices are the points. So the vertices are the points of the triangle. So that would be points A, B, and C. The sides are the segments that are connecting. So the sides here would be segment A, B. B's and 3's are hard with this stylus. Segment A, B, segment B, C, and segment A, C. Those would be our sides. Okay. We can classify triangles according to either their sides or their angles. So that's actually what a big chunk of our vocab here is. Scalene, isosceles, and equilateral. These are all ways to classify our angles by their sides. A scalene triangle says if a triangle is scalene, that it has no congruent sides. So none of the sides would be congruent to each other. If a triangle is isosceles, it says if a triangle is isosceles, then it has at least 2 congruent sides. Keyword there being at least. Okay, so make sure you pay attention to that phrasing, at least 2 congruent sides. Oftentimes they'll look something like this, where you'll have your 2 congruent sides marked. And let's make a prediction here. If you have 2 congruent sides, what else do you think you might have? Carly? 2 congruent angles, and those angles are always the ones across from those congruent sides. So if you have congruent sides, you're going to be able to imply that you have congruent angles as well. Equilateral says if a triangle is equilateral, then all 3 sides are congruent. Now, if all 3 sides are congruent, think about what Carly just said. What do you think we'll be able to imply? Brennan? That all 3 angles will also be congruent. Absolutely. Okay. Then we can also classify our triangles according to their angles. We can have acute triangles. That's not an I there, by the way. I know how to spell angle, I promise. It's just a little mark. There we go. An acute triangle is acute if it has 3 acute angles. So all 3 must be acute for it to be acute. Obtuse triangle means it's going to have just 1 obtuse angle. Think about it logically. Would it make sense for a triangle to have 2 obtuse angles? Think about what a triangle looks like. It wouldn't close, is what would happen. You wouldn't be able to connect all your sides. A right triangle means it has exactly 1 right angle. Same idea. Can you even imagine a triangle with 2 right angles? It wouldn't make sense, okay? And then equiangular. If a triangle is equiangular, then all 3 angles are congruent. And remember, if it's equiangular, it's also going to be equilateral. Those 2 things always go hand in hand. So often what that will look like is you'll have your triangle. All 3 sides will be marked as congruent. And if all 3 sides are congruent, all 3 angles will also be congruent. So those 2 things always go together. Okay. Then we have something called the auxiliary line. If a line, segment, or ray is auxiliary, then it is added to a diagram to help in a proof. I think there was actually one in your homework that you had to add a little segment in it to split a picture in half. I don't know if you guys remember that. That would technically be an auxiliary line. It's a line that doesn't technically exist in your picture, but you're allowed to draw it to kind of imply some additional information about a picture. And then we have corollary. That is, if a statement is a corollary, then it can be proved easily by applying a theorem. So it's not something you technically need to like sit there and work out and prove, but it's something you can quickly imply based on information you're given. And these are, you're allowed to use these as reasons and proofs, okay? And before our chapter 3 test, I will be giving you guys an updated vocab sheet to add on to chapter 3. Hopefully I can link it in tomorrow, okay? Oh, this computer is fine. No, I just want to be able to give you guys one so you can use it going forward. If I don't have time for tomorrow, then later in the week you'll get one. So we have 2 theorems today. The first one is the triangle angle sum theorem. That says the sum of the measures of the angles of a triangle is 180 degrees. That's actually probably something you already knew, okay? But now it's an actual theorem. We can use it in proofs. And we're actually going to prove it. We're going to practice our proofs with this. So what this says is we are simply given triangle ABC. We just know it exists. We want to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. Now, in order to do that, we want to look for other things that we might know in this picture. So if you just take a look at your diagram, we have to figure out a way to get 180. It doesn't just like magically appear. Does anyone notice something else in this picture that could possibly give us 180 degrees that we can then use, Maya? Yeah, if you take a look, if you drew, and I went ahead and put this part in your proof for you, but through point B, you can draw an auxiliary line, BD, that's parallel to AC. Now, the reason you know it's going to also be parallel, we had a little theorem last class. It doesn't have like a fancy name or anything, but if you have a point outside of a line, there's exactly one line that could go through that point that's parallel to the one given to you. And that's our reasoning behind why we can do that. So we would then know that these 2 lines here are parallel. Now, if those 2 lines are parallel, we'll have angle relationships and things like that, right? So we have a straight line, which means we'll have what kind of an angle? A straight angle. And could a straight angle be helpful in creating 180 degrees? Absolutely. If I took the measure of angle 4 plus 2 plus 5, shouldn't that give me 180 degrees? Yes. So that's how I'm going to get that, except, great, 3 angles adding up to be 180, but they're not the right ones. Do you guys notice anything else in your picture that might allow me to add up the correct angles to be 180? Maybe with some substitution. Carly? So for this one, so here how that would work, so with 1 and 2, they do have a transversal right here, but angle 2 is actually formed by segment BA and segment BC. And angle 1 is formed by segment BA and segment AC. So they actually, they are same side interior, but they would not be supplementary because they're not formed by the 2 parallel lines. Angle 2 is not formed by the parallel line. Plus 2, if you think about it, Carly, if it's a triangle, all 3 are going to have to add to be 180. It wouldn't make sense for just 2 of them to. Does that kind of make sense? Okay. But there is an angle relationship. Does anyone see which one it might be, Megan? Yeah. Angles 1 and 4 are alternate interiors. Do you guys see another set? Yeah, 5 and 3. Right here. And then those will be congruent. So then in your equation, you can substitute 4 with 1 and 3 with 5. Okay, so let's try that out. Let's see what it looks like. So first thing we need to do is create our equation of three angles adding to be 180. They won't be the right ones at first, but then we'll do some substitution. So what we're going to do here, angle 4, 2, and 5, they're going to form our straight angle here, but we can't go to that right away because there is no label here for that third point, is there? Do you guys notice that? Okay, so what we're actually going to have to do is add up some parts separately. The first thing we're going to do is say that the measure of angle DBC equals the measure of angle 4 plus the measure of angle 2, because that's part of our straight angle. Okay. Now, what lets you take parts of angles and add them up? Anne-Marie? Very good. That is the angle addition postulate. Okay. Now, the reason we want to do that, yes, Brock? Absolutely.
How come, like you already know that 1, 2, and 3 equal 180 degrees triangle, and it says.
We're proving that theorem, though.
So there's no theorem that says like 3 sides of the triangle.
Well, the 3 angles would equal. That is this theorem. We're proving why it works.
Oh, you're proving.
Yeah, we're proving the theorem. Yes. Oh, yeah. No, we're physically proving this theorem right now. Does that make sense? Okay. Were you like, why are we wasting our time doing this? We're proving the theorem. It's just good proof practice. Okay. So yeah, we're just proving why it works. And it's nice because it has different components in it, like angle addition, alternate interior angles, just to practice some of those definitions. So our angle addition postulate, guys, remember there's 2 different ways you can, or there's 2 parts to it. But it's always adding up 2 angles. That's why we're not going right to that to the 3 angles. Angle addition postulate is always like 1 angle plus another angle, okay, equals a whole angle. So the next thing I'm going to do is say that the measure of angle DBC plus angle 5 equals 180, because that's what's forming my straight angle up there. So the measure of angle DBC plus the measure of angle 5 equals 180. That's that second part of our angle addition postulate that lets you say if you see a straight angle, you can add it up to 180. So that's also the angle addition postulate. Okay. Now the reason behind this, right now we have 2 angles adding to be 180, but in this line here, doesn't angle DBC equal the measure of angle 4 plus the measure of angle 2? So what could I do with that information to rewrite my equation, Maya? Very good. I can substitute that in. The measure of angle 4 plus the measure of angle 2 plus the measure of angle 5 equals 180. Good. And that would be substitution. Okay, now I have 3 angles adding to be 180, but I don't want it to be 4, 2, and 5. I want it to be 1, 2, and 3. Brennan? Yeah, you're welcome. So for this one, angle 4 was congruent to what other angle? 1, because of why? What was their angle relationship? Yeah, alternate interior. So we're going to say that angle 1 is congruent to angle 4. Could we do that with another set as well in the same step? Which other ones did we have? Carly? Angle 3 and 5. We're also going to say angle 3 is congruent to 5. And that's okay to do all in one step because these are both alternate interior angles. So alternate interior angle theorem. People at home, just so you know, my other computer died, so I can't see the chat. So if you need something, just yell at me through my speakers. All right, so now we have that they're congruent, but is it ready to be substituted in yet? Why not, Grace? They're congruent, but if they're congruent, can I now convert it to be equal? Yeah, so that's what we need to do next, convert it to be equal. The measure of angle 1 equals the measure of angle 4, and the measure of angle 3 equals the measure of angle 5. And that would be the definition of congruent angles. That's what lets you switch. Okay. Now is it ready to be substituted? Yes. So now we can take this information that we had here. We have that the measure of angle 4 is equal to the measure of angle 1. And we have that the measure of angle 5 is equal to the measure of angle 3. So we can take that and substitute it in. So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. Okay. I figured we needed a little proof practice. Questions on that? Reagan? I mean, we did some algebra. You did some algebra on your homework last night. Systems of equations, right? No, because this is geometry. I mean, not really. There's equations. I see equations in there. That is true. There is a lot of vocab in geometry, and I would say what a lot of geometry is going to end up being is taking geometry vocab and setting up algebra equations based on the vocab. That is what a lot of geometry tends to be. Sorry, Reagan. All right, so last theorem is the alternate exterior angle theorem. We're not going to prove this one. This one says that the measure of an exterior angle of, I should say of a triangle equals the sum of the measures of the two remote interior angles. If you take a look here, an auxiliary line was drawn to extend this triangle out to make angle 4. So what this theorem is saying is that the measure of angle 4 equals the measure of the two remote interior angles. That means the ones not adjacent to it. So the ones on the other side of your triangle, which would be angle 2 and 1. So the measure of angle 1 plus the measure of angle 2. That's what this theorem says. Okay. Questions about any of the vocab? The rest is just, well, I guess we have some corollaries. Anything on the front though? No? Okay. So the last like vocab type thing is corollaries for today. These are things that can be applied from the theorems we just learned. The first one, and these don't have formal names, so if you want to use them in a proof, just like write a statement. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. I often refer to this as like the third angle corollary. Okay, what this is basically saying is in two triangles, if you have the two sets of the angles are already congruent, you can imply the third one automatically is, because aren't the angles going to have to add to be 180? So like in this picture here, we have that angle B is congruent to E. They're both 45 degrees. Is there another set of angles that we'll know is congruent? Megan? There are vertical angles. Vertical angles are always, always, always congruent. So we'll also have those. So there's two sets of congruent angles. And if those two sets are already congruent, then we can then imply that angle A would be congruent to angle D. Okay, it's just a nice way to be able to imply something without having to do all that extra work for it. The next one says, if each angle of a triangle, or I'm sorry, each angle of an equiangular triangle has a measure of 60 degrees. Because if it's equiangular, what does that mean about all the angles? They're congruent. And if an angle, or if a triangle has a sum of 180 degrees and you split that into 3 congruent parts, each one will have to be 60. In a triangle, there can be at most one right or obtuse angle. That has to do with the sum. If the sum can only be 180 degrees, right? Can you have 2 right angles? That'd be 90 plus 90, which is already 180, right? Same thing with if they were obtuse. Your sum would be greater than 180. It wouldn't make sense. And then the last corollary is that the acute angles of a triangle are complementary, or of a right triangle. So if you have a right triangle, something like this, I'll call this triangle A, B, C. So if you have a right triangle, one angle is already 90 degrees, yes? The sum of all 3 angles has to be what? 180. So if the sum is 180 and one angle is already 90, what's 180 minus 90? 90. So wouldn't the other 2 angles have to add to be 90 degrees? That's what this corollary is saying. If angle C is already 90 degrees, then that means all that's left in your triangle is an additional 90 degrees. So the measure of angle A plus the measure of angle B would have to be 90, which means that they're complementary. Okay. Questions about our corollaries? Okay, we just have a few examples. The first example is an always, sometimes, or never. If a triangle is isosceles, then it is equilateral, always, sometimes, or never. What do you think, Olivia? Sometimes, absolutely. Because if you go to your vocab, this one can be tricky because it can seem like a never, because you're like, oh, isosceles means there's 2 congruent. But if you go to your vocab, doesn't it say at least 2? So that means it's sometimes. So you just make sure you pay attention to that little bit of vocab there. If a triangle is equilateral, then it is isosceles. What about this one? Justin? So for this one, think about it's like that previous statement but flipped around, isn't it? So if it's isosceles, then it's equilateral. That one's sometimes, because an isosceles triangle could be equilateral. But if you reverse it, if it's equilateral, isn't it automatically going to also be isosceles? Because an isosceles is at least 2 congruent. An equilateral means that all 3 are congruent. If all 3 are congruent, won't at least 2 for sure be congruent? So this one would actually be always. Does that make sense, Justin? Yeah, okay. Those 2 are a little bit tricky. So you got to remember, if at least 2 are congruent, then 3 could be. That's why it's sometimes. And for the second one, if 3 are congruent, then for sure at least 2 are. That's why it's always. Then for part C, if a triangle is scalene, then it's isosceles. Always, sometimes, or never. Brock? That one's never. Because if it's scalene, aren't all 3 different? And if it's isosceles, at least 2 are the same. You can't have those 2 things happening at once. That one is never. And last one, if a triangle is obtuse, then it is isosceles. If it is obtuse, then it is isosceles. Ayla? Sometimes, good. If it's obtuse, that just means there's one obtuse angle. Could it be obtuse and isosceles? Sure, but could it also be obtuse and scalene? Yeah, so it's a sometimes. Good. Questions on those? All right, Part 2, complete the following based on the figure to the right. There's one very similar on your homework, so I just wanted to make sure how we were doing okay with reading our diagram. The measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 will have to equal what? Anne-Marie? 180. All right, good. Yep, that one's just our theorem. All three angles are going to have a sum of 180. If the measure of angle 2 equals the measure of angle 3, I'm sorry, if the measure of angle 1 equals the measure of angle 2 equals the measure of angle 3, then the triangle is what? Melissa? Equiangular as well as equilateral. Yes, this one it will be both. Remember, one implies the other with those. So the triangle is equiangular and equilateral. Okay, good. The measure of angle 4 equals the measure of angle 2 plus what other angle? This was our other theorem that we learned today. Oh, Carly? Angle 3, very good. This was our triangle exterior angle theorem. Good. And then for part D, this one says that the measure of angle 1 is x squared. The measure of angle 2 is 7x, and the measure of angle 3 is 4x. Solve for x. All right, what would we have to do to set this problem up? Carly? Very good. All of these are interior angles, so we're going to add up all three, set it equal to 180. So that would be x squared plus 7x plus 4x equals 180. Reagan? Very good. Why do I have to do that, Reagan? Very good. Yes, this problem wants us to factor, and in order to factor, you need to have your like terms combined, and it needs to be set equal to 0. Now, the big question is, when do you factor, right? How do I know I have to factor? How did you know you had to factor this one, Reagan? Because there was an x squared. What else, Brennan? There's also a regular x term, and then there's also constants, right? So the x squared should definitely stick out to you. X squared means you can't just solve this like a normal equation. You're either going to need to factor, do the quadratic formula, or solve by taking square roots. Now with this one, there's also regular x terms. So solving by taking square roots is out. Factoring our quadratic formula is in. Quadratic formula is above Reagan, okay? But I don't recommend it. Well, I mean, it's fine. It works. The nice thing about the quadratic formula is it works for everything. Literally, it works for all of them, which is lovely about it. However, it takes like 500 years to do. So I would probably stick with factoring when possible. It's not always possible, but when possible, it's what I would do. So we're going to combine our like terms. Why are you turning off? There we go. We are going to combine our like terms, and we are going to move that 180 over like Reagan suggested. Okay, what would I do now to continue my factoring? Carly? Yeah, very good. Yeah, well, so I always like to put my blank parentheses, right? Give me something to work with. And I always like to throw my x's in there too, because x times x is x squared. But then, yeah, you said we're looking for factors of what? I'm sorry. Of 180, yes. We're looking for factors of 180. That means two numbers that multiply to be 180 that also do what at the same time? Add or subtract to be 11. So if you can think of it right off the top of your head, awesome, good. What should you do if you cannot? Brennan. That's what I would do. Yeah, 180 hopefully shouldn't be too hard, but sometimes you might get a weird number, right? So if you're not sure, write it out, right? 1 times 180, 2 times 90, 3 times 60, and so forth. Use your calculator. You're allowed to divide stuff out. Does anyone know two numbers that would multiply to be 180 and add or subtract to be 11? Mike? Yeah, I would start, I again, just to take it step by step, if you're good with factoring and you can go ahead and put your signs in right away, do that. But if not, I would throw the 20 in one and the 9 in the other, and then figure out your signs from there. Because you know that 20 times 9 is 180. And if you take 20 minus 9, it could give you an 11. And then, Mike, what did you say your signs needed to be? Yeah, a -9 and a +20. Because 20 times -9 is -180. 20 minus 9 is 11. This is great. It's factored. How do I then get my final answers? Melissa? Yes, I said each individual part equal to 0. So x plus 20 equals 0, and x minus 9 equals 0. That is going to give me final answers of x equals -20 and x equals 9. From there, what should you always double check? What do we need to confirm, Brennan? Yeah, very good. Take these and make sure that they make sense. They don't both necessarily work. Sometimes they do, sometimes they don't, sometimes it's just one of them. So always plug it in and check. In this situation, will -20 be logical? No, why not? Olivia? Well, if it's negative, last class we had a negative and it worked out. Oh, yeah, we can't have a negative angle. If you plug -20 in, let's say for angle 3, that's going to give you -80, right? That's no good. Plus, if you plug it in for x squared, that's a 400-degree angle. That's not going to work, okay? But would 9 be logical? Yeah, that would give you 81. That would give you 63, and that would give you 36. And it could even be a good idea at the end to add those up, make sure they equal 180. Reagan? If both of them works, then you'll just have two different answers. Yeah, and if it's a situation where, especially like if it's a Canvas thing and there's two different answers, I would have two like spaces for it. So like you'd be able to put in both. Yeah. But that could happen sometimes. I think the one we did last class worked for both. Okay, questions on that? Are we feeling a little better about factoring now that we've practiced it a little together? Okay, my goal is hopefully to do some more challenging ones together at some point. We just have to find a day where there's a little extra time, or maybe I'll just like make a little instructional video and post it on Canvas. So if you guys have the time, you can watch it. All right, last one. Oh, that didn't sound good. All right. So last one, solve for x and y. We have a diagram here with a 50-degree angle, a 60-degree angle, an external angle of x, and then 45 and y. There is almost always more than one good way to do these. So does anyone have any suggestions of a place we could start? Anne-Marie. Like this one here? Okay. Sure, we could do that. So we could take 180 and subtract our two given angles, 50 plus 60. That would give you 70, absolutely. What could you then do from there? Brennan? Well, so you would add which ones together? The 50 and the 70. So for that one, you don't actually need to add those ones together. We're using, like going off the strategy that Anne-Marie had, we actually now have a linear pair here. So you could just subtract from 180. So like you could do x equals 180 minus 70, which would be 110. Right? That's one way. Does anyone have another way we could solve for x That would take us right to the answer. Mike? Yeah, we could also apply our triangle exterior angle theorem. X is exterior, right? 50 and 60 are our remote interior angles. So another good way to do this would be X equals 50 plus 60, which would also give you 110. Either way is fine. They're both using theorems that we've learned, and either works. Does that make sense, guys? Okay. So either way, that's 110. Any ideas of how we could then solve for y? Reagan? Oh, okay. Add 70 and 45. Yeah, no, that's okay. So you have vertical angles here. So this angle would also be 70. And then all three interior angles have to add to be 180. So that would definitely work. So you could do y equals 180 minus what you have so far, which is 45 and 70. And you said that would give you 65? Sounds good to me. Any other strategies? I see one other way that we could do that one. It's applying a different theorem, though. It's sometimes not as obvious, but it's a good strategy to know because depending on the information you're given, you might have to use it. Libby? You do have alternate interior angles. We don't know that they're congruent, though, because our lines aren't parallel. But if you did have parallel lines, then yes. With this one, we could actually kind of reverse our triangle exterior angle theorem. We now know the exterior is 110, and we have one of our remote interiors. You can just work backwards to find y by subtracting. Because shouldn't x equal y plus 45? So 110 equals y plus 45. You could subtract that instead. Or you could do y equals 110 minus 45. And that would still give you 65. So that's a good strategy as well. They're both good to know because, again, depending on the information you have, you might have to apply one or the other. Good. Questions? Yes. 110 minus 45. Okay. So here, your exterior angle, which is 110, equals the two remote interior angles added together. So 110 equals y plus 45. So you would work backwards and just subtract instead since you're looking for the interior. Does that make sense? Okay, that's a good question. Anything else, guys? How are we feeling about this? Reagan, yes.